All right, welcome everybody. We're going to be going over the rules of exponents today. This is the guided notes. If you don't have the guided notes, please at least pull them up on your laptop at some point. You can follow along on a regular sheet of paper too. I'm going to be going over all of the examples and the rules that we have here so that you can be successful in completing the rest of this unit's assignments. Okay, so starting off, the rules of exponents. What are exponents, right? So usually whenever we talk about exponents, people think about this little number that's above the big number. It's to the upper right of what's called the base. So this is the base number, and it's the big one. This is the exponent, and it's the little number. Altogether, this is usually referred to as the power. Now, if you've grown up thinking that the little number is the power, don't worry too much about changing that. Just know that sometimes if we're referencing the power, what we're referencing is the whole thing. When we talk about the exponent, that's going to be the little number, and we're going to talk about the base a lot because most of these rules involve having common bases. So everything is a 5 for a base, or everything is an x for a base. And so we'll be talking about that. So understanding that basic vocabulary is our first step. Let's talk about what's called the product of powers. The product of powers is simply product, which is multiplication, of powers. So it's multiplying things that have powers. Now, this kind of applies if they have a common base. So the rule says on the guided notes, it says if I have a thing to a power times another thing to a different power, that what I'm going to do is add those powers together. And so let's try that with our first example. Now, in order to be successful with this, please make sure that you're familiar with exponential form, expanded form, and standard form. If you need a refresher on that, please go back and find that video. We're going to keep moving forward though. So I'm going to do it both ways. I'm going to use the formula for the exponential version, and then I'm going to use the expanded version, and we will compare our answers there. So the first example says 5 squared times 5 to the 6th. Please recognize that 5 squared means that it's 5 multiplied to itself 2 times. So that's going to be 5 times 5. Now, I'm going to multiply that by, oh, sorry, I said I was going to use the exponential form first, huh? Sorry, so let's follow the rule. 5 squared times 5 to the 6th means 5, just like it's A, and A. I'm going to keep my base, and my base is 5. 5 to the 2 plus 6. Okay, so this is just us following the rule with the example, right? So 5 squared times 5 to the 6th, they have the same base, they're being multiplied, so I'm going to add those exponents. Okay, make sure you're following along with this. So if I do it in the expanded form, I have 2 5s multiplied together times 6 more 5s multiplied together. So how many y's do I have, or how many 5s do I have multiplied together? Well, let's count them. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's go back up here to our exponential problem. We can actually do 2 plus 6, right? So this ends up being 5 to the 8th. Now down here, we're multiplying all these 5s together, but again, there's 8 5s, so that's 5 to the 8th. So we get the same answer whether we do this in the exponential form using our formula or whether we use the expanded form. Let's go ahead and try another example. I'm actually going to go through these a little bit faster. So please make sure and follow along, pause, rewind, whatever you need to do, okay? So I've got y to the 4th times y to the 3rd times y. Now everybody remembers the rule and they immediately say, oh, that's y to the 7th, because it's 4 plus 3, right? And there's no exponent on the other one. Something to keep in mind is that if there is no visible exponent, how many y's are multiplied together right there? There is one y, right? There's still one y there, and so we can use the exponent of 1. So following our rule, this becomes y to the 4 plus 3 plus 1, and that ends up being y to the 8th. Let me bring my brush size down a little bit, just because since we're working with exponents, that'll be useful for us. Okay, let's try expanded form. Y to the 4th times y to the 3rd times y. How many y's are in a row? Well, there are 8 y's in a row. So this is also y to the 8th. So no matter which method you use, you're going to be fine. Now, I would recommend that if you're not very familiar with all of this, when we do quizzes and tests and things like that, that you use the expanded form. I'm going to make sure that we keep the number of exponents down, and we will just move on from there, okay? All right. So that you can use the expanded form without having to go crazy writing out all the exponents. Okay, next example. 7y to the 5th times 6y. Okay, you may hear a bell ring here in a couple of minutes. All the kids are going to be getting out of class, but just bear with me. We're going to keep moving on because this is kind of a long lesson. It's hard to find a good spot to record it. Okay, so using our formula, only things that have a common base and have exponents are the things that we're going to multiply together. So we have 7 times a 6. I'm just going to rearrange things a little bit so that I can put my y's all together. Y to the 5th plus 1, right? Because there is one y right here. And so that ends up being 42, because we can actually multiply 6 times 7 without the numbers being crazy. Y to the 6th. Okay, expanded mode. 7, 5y's times 6 and 1y. I can still do, this is combining like terms, I can still combine my 7 and my 6, and that's still going to give me 42 y to the 6th. Moving on, pause if you need to. Parentheses, -3 x squared y to the 7th times 5 x y to the 6th. Now to save time here, I'm not going to do the expanded form. I'm just going to do the exponential rule. So the exponential rule says that for common bases, so my x's are the same and my y's are the same, I can multiply them together. Now my numbers I'm just going to put out in front, save them for later, for when I need to simplify. And then I have x to the 2, and there's actually a 1 right here, right, to the 2 plus 1, and y to the 7 plus 6. So -3 times 5 is going to be 15. X to the 2 plus 1 is going to be x to the 3rd. Y to the 7 plus 6 is going to be y to the 13th. Okay, now if we went on expanded form, it would still be easy to see that I have 2 x's right here that are expanded out, and then one more x right here, so it would be 3 x's. And then here are 7 y's, here are 6 y's, so that's going to end up being 13 y's. Now again, on the expanded form of the test, I'm not going to make you write out 13 y's, okay? So moving on. I'm going to move on to the next section. So that's all of the product of powers examples. Quotient of powers. Quotient means to divide. So we're dividing things that have powers, but they have the same base, okay? Here we go. The rule says if I have a thing to a power divided by that same thing to a different power, so remember when we had the product, a to the m times a to the n, that we would just end up adding the exponents, right? A to the m plus n. So what do you think we're going to do now that we're dividing things that have exponents and a common base? Right, so we are going to, we'll still have the common base, but we're going to subtract those exponents. Now, the order that you subtract in is very, very important. Adding, order doesn't matter. Multiplying, order doesn't matter. Subtracting and dividing, you bet it matters. So be very careful that you are starting off with the exponent in the numerator and subtracting the exponent in the denominator. So we're starting off with the exponent in the numerator, and then we're ending up with the exponent in the denominator. Let's try an example. So we have this one that says y to the sixth divided by y. Following our rule, we're still going to have a y, and we're going to subtract the exponents. 6 minus 1. How many y's are down here? There's one y down here, right? So 6 minus 1 is 5, so this ends up being y to the fifth. All right, I'm going to bring my brush size back down so that I can fit more on the page. Let's go ahead and move on to the second example. Pause and rewind if you need to. Here we go. This one says 6 to the 13th over 6 to the 2nd. Again, I could use my expanded form here, but that's going to take forever. So what I'm going to do instead is just follow the exponential rule. So this ends up being 6 to the 13 minus 2. Now, if you really did want to do 6 times 6 times 6 times 6 times 6 and go on forever with that, divided by the 6 times 6, let's see, there's 1, 2, 3, 4, 5, so we'd still need a bunch more. I don't even have room for them all. Just dot, 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 because that continues for a while. What we need to do in expanded form is eliminate ones that are the same on the top and the bottom, because 6 divided by 6 is just 1. So we're making ones out of these 6's that are the same on the top and the bottom. And what we would end up with is 6 to the 11th. And down here we would still have 6 to the 11th. We would have no more 6's on the bottom. We would have 11 6's on the top. And so they would both reduce to 6 to the 11th. All right, so we've got the music going on in the background because class is about to start. You will hear a bell again, and then we'll keep moving forward. I'm going to go ahead and write the next problem, though, while we're waiting for the bell, because this one takes a little bit of writing. So 10, 8 to the 7th, b to the 9th. Hopefully YouTube doesn't remove this video just because it has some bell music in it. 15, a to the 5th, b to the 9th. Okay, again, I'm not going to expand this out just because there's way too many letters, but let's see what happens. So the 10 over 15 we can simplify by itself. We could do it now or we could do it later. It doesn't really matter when you do it. We could even parse this out into separate objects. So I could say 10 over 15 times a to the 7th over a to the 5th times b to the 9th over b to the 9th. Now you might recognize that there's the same number of b's on the top and the bottom, and so all those b's are going to go away. But let's follow our rules to see what happens. So 10 over 15 simplifies, both of those are divisible by 5. 5 goes into 10 twice. 5 goes into 15 3 times, times a to the 7 minus 5 times b to the 9 minus 9. Now this is going to come in handy later as well. Okay, let's keep going. So we've got 2/3. 7 minus 5 is 2, so 2/3 a squared. Oops. B to the 9 minus 9 is 0. So I have no more b's. All my b's got canceled out. So something to remember for this next section is that b to the 0 does not equal 0. If it did equal 0, it would negate everything else that it's multiplied to. B to the 0 equals 1. Because what happened is we had a bunch of b's on the top and a bunch of b's on the bottom, and we turned them all into 1s. So this ends up being 1 times 1 times 1. And then 1 times 1 times 1 is just 1, and 1 times stuff is just stuff. So 1 times anything is just whatever the other thing is. So they don't go away. When we say canceled out, they don't disappear. They turn into a 1, and that's going to be incredibly important for later assignments. All right, moving on. So my final answer to all of this is, really is 2/3 a to the second. So this up here and that down there, they are the same. We didn't change anything. Well, sorry, we changed its form, but nothing magically appeared or disappeared. In math, everything's retained. It's like the conservation of energy or the conservation of mass. All mass and energy is retained. It just changes form. Okay, moving on. So that is the quotient of powers. Let's talk about zero exponents. We already got introduced to it. The idea with zero exponents is that anything to the 0 power is always 1 forever. That's it. That's the whole rule. Anything to a 0 power is 1. Anything to a 0 power is not 0. Don't say it's 0 because it's not. It does go away, but that's because it turns into one of those ninja ones, right? So if I have an x, I can multiply that by 1. I can divide it by 1. It's to the first power. There's a bunch of ninja ones everywhere, right? But they're hidden most of the time because that's what we're assuming. We assume that its exponent is 1. We assume that it's times 1. We assume that it's divided by 1. And we use that information to our benefit sometimes. Okay, so anything to the 0 power is 1 always. So that's why there's only 2 examples of this. So let's try it. So no matter what it is, there's 3 examples. So let's say I have 8 squared over 8 squared. I'm going to do this using both the rules of exponents and expansion. So 8 squared divided by 8 squared is going to be 8 to the 2 minus 2, right, which is 8 to the 0. Now we know because the paper told us so that that equals 1. Let's take a look at why that is using the expanded version. So we've got 8 times 8, that's what 8 squared means, over 8 times 8, that's what 8 squared means. Anything divided by itself is 1, and so that turns into a 1. Anything divided by itself is 1, so 1 times 1 is just 1. This is why everything to the 0 power is 1, because everything cancels out, essentially, and leaves you with a 1. And 1 times stuff is just stuff. So, hopefully that helps you. If it doesn't, please go rewatch it. Moving on. So everything to the 0 power is 1. So even if I had something like negative 3x plus 7 all to the 0 power, the 0 power is being applied to everything. And so everything turns into a 1. Next up, let's look at the last example that says 8x to the 0 plus 5. 8x to the 0 plus 5. What's being taken to the 0 power? It's just the x. It's not the 8. It's not 5. There's no parentheses anywhere to group them all together. Only the x is being taken to the 0 power. So things to the 0 power are just 1, and so this ends up being 8 times 1 plus 5. We can use order of operations now, which is why I stressed that so much in the beginning. 8 times 1 is 8, plus 5 is 13. And so our answer is simply 13 for that last example. Again, anything to the 0 power is 1. That does not mean that everything else is also 1. Only the things that are being taken to the 0 power. Okay, moving on, negative exponents. Negative exponents are a little bit tricky, but that's why we're taking care of them here in the middle instead of at the beginning. Negative exponents essentially say if I have a thing to a negative exponent, that is the same as 1 over that thing to a positive exponent. So remember how I said we always assume that everything is divided by 1? So what we did is we essentially took this stuff and we put it in the denominator. We put it in the bottom of the fraction. So conversely, if I have a negative exponent on the bottom of a fraction, that will move to the top, to the numerator. So that equals a to the n. And you could say a to the n over 1, or you could just say a to the n. Either one is fine. Okay, take a good look. Pause it if you need to. I'm going to move on. So let's explore how this works. So we've got b squared over b to the 5th. So I have 2 b's on top. Oops, sorry. Let's do this the algebraic way, the exponential form way first. B to the 2 minus 5 equals b to the negative 3. Make sure it's a negative 3 and not a positive 3 when you get your answer, yeah? Because the 5 is bigger and we're subtracting the bigger number. Okay, expanded form. Let's try that. So it's b times b on the top, and then 5 b's multiplied together on the bottom. 3, 4, 5. Let me bring my fraction line out. Okay, anything the same on the top and the bottom is just 1. B divided by b is 1. B divided by b is 1. Okay, let me warn you. This is the mistake that most people make, and they'll say, oh, that means that I have b to the 3rd. That's incorrect. Because where are my b's? Are they on the top? No, my b's are on the bottom, right? Let's back this up. So, my students say, what's on the top then? Well, you turn those b's into 1s, right? So this is essentially 1 times 1 over 1 times 1 times b times, oops, b times b. Sorry about my awful handwriting. And so I still have a 1 on top, and I have 3 b's on the bottom, which I can rewrite as b to the 3rd. So we've just shown that negative exponents means you're just going to move the base and the exponent. You're going to move the whole power, but you're going to lose the negative on the exponent. We didn't change the sign on the b. We only changed the sign on the exponent when we move it. We don't change the sign on any coefficients that get moved, just on the exponent. That one's tricky, so go back and watch it again if you need to. I'm going to keep moving forward. So, 2 to the negative 3rd. Just like we said, you can either say, well, okay, well, that's over 1. And so I'm going to take this whole thing because that's what's being taken to the negative 3rd, and I'm going to move it down here. And we end up with 1 over 2 to the 3rd. Now, if you go the extra mile and you say, okay, well, that's 1 over 8, that's great, that's fine. I'll take both answers. These are both correct, okay? Great. All right, and then the next example, again, if I have a negative on my base and a negative exponent, remember that only the exponent changes. See this negative? It's still there. This negative, so the negatives were still there. When we did it on the other ones, they didn't change from positive to negative. Only the exponent changes signs, right? Okay. So that's negative exponents. Let me give you one more example that's not in the notes just because this is going to be one of the more confusing topics. So let's say I have a to the negative 2, b to the third over a squared b to the negative 2. Okay. So this is where things get tricky because now we have multiple negative exponents, we have multiple positive exponents, and we have multiple variables, right? Just do it one step at a time. You can split it out if you need to. Let's just deal with the numbers. There are no numbers. That was easy. Sorry, I meant base numbers, coefficients. But there are still exponents, right? So let's start with A. Let's just work on the A's. So I recognize that this a to the negative 2, that it's the a that's being taken to the negative 2, and so the a will move down here. The b up top does not have a negative exponent, so that will not move. But this b down here does have a negative exponent, so that's going to go to the top. Okay, let's see what we end up with when we do that. So I have my fraction line, I have my b to the third, which was already up here. Sorry, let me rewrite that so that's more legible. B to the third up in the numerator, joined now by a b to the second. And I can write that with my green because I actually used green. So my b to the third times b to the second. And then on the bottom I already had an a squared, joined now by another a squared. So let's simplify this now. B to the third times b to the second is going to be b to the 3 plus 2. A squared times a squared is going to be a to the 2 plus 2, using our previous rules. And so now we have b to the 5th over a to the 4th. Now you may want to write that example down somewhere because the worksheet, quizzes, and the tests will all have multiple variables, maybe multiple negative exponents, maybe zero exponents and positive exponents mixed in. And so this is going to be your most useful example so long as you understand everything so far. Okay, 2 more rules. Hang in there. Pause it, take a break if you need to. You can always, it's not live, right? You can always take a break and come back. Rules of exponents, power to a power. So power to a power says that I have something that is a power being taken to another exponent. So the rule says if I have a to the m to the n, so my power is being taken to another exponent, another power. Instead of adding those exponents, we are going to multiply them. So a to the m times n. Let's practice that. So I have x squared to the 8th. I'm actually going to do this in both exponential form and expanded form so you can see it. We are going to multiply them, x to the 2 times 8, which is going to be x to the 16th. Oh goodness, I regret saying that I was going to write this out. Okay, but let's do this. How many x squareds are multiplied together? The whole x squared is my base, and there are 8 of them. There are 8 x squareds. So this translates into x squared times x squared times x squared, and there are 8 of these, x squared, and this is our expanded form, which will never fail you. And then I've got 4 more. Let's see if I can speed it up a little bit. Great. Except now I can expand it out one more time. Shoot. It looks like I'm running out of room down here at the bottom, but let's give this a shot. So here's two x's, here's two x's, 2, 2, 2, 2, 2, 2. So I'm going to expand all those out. And I'm going to do it up here at the top, actually. So there's 2 times there's 2 times there's 2. So that's half of it, right? There's 2, there's 2, there's 2, and there's 2. Goodness, that's a lot, right? So how many x's do we have in total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is still using exponential form, x to the 16th. Woo! We made it. So keeping in mind that exponents just mean this is how many of those things are multiplied together. Always start with the outermost. How many x squareds did I have? I had 8. And so I can either follow the rule or I can actually expand it out. And if you need to expand it out again, there's no shame in that. It might take a little longer, or in some cases a lot longer, like it did here, but it will never fail you. Expanded form will never fail you. Okay, here we go. Still going. My computer went to sleep. So when I stop this video, there will be a little bit of lag time there. Actually, I should log in and make sure this is still recording. I apologize if you get this as junk. Great. 30 minutes. Oh my word. Okay. Next example. Y to the negative third to the negative fourth. This is where things get funky. Ready? So, how many y to the negative thirds do I have? I have negative 4 of them. How do I get rid of that negative? Well, I'm going to send it to the denominator, right? So this equals y to the negative third, oops, 1 over y to the negative third to the fourth. And then I could say, well, okay, except all of those are going to be negative. So now I'm going to put them back on the top, and I could say y to the third to the fourth. Now, some of you that are really smart cookies and whose brains are still intact by this point will say, Mr. Reynolds, you could have just left it there. And I would say yes. So without using the expanded rule, we multiply our exponents together. This is y to the negative third times negative fourth. And you would get y to the 12th. And it's on the top, right? It's not on the bottom. We have no more negative exponents. And this would also be y to the 12th. Now I'm not going to write it out in expanded form, but let me show you what the first step would look like. You would say, okay, well, how many y to the negative thirds do I have? Well, I have negative 4 of them. So this is the same as 1 over y to the negative third times y to the negative third times y to the negative third. Do I even have enough room? Y to the negative third. Dealing with these is kind of an endurance race if you're using the expanded form, but it will always lead you right if you forget what the rules are. And so then all of these y to the negative thirds would go back to the top, right? So all of these would go right back to the top. And they would be y to the third, y to the third, y to the third, y to the third, and it would still be y to the 12th. Moving on. Power of a product. Power of a product says, find the power of each factor in the parentheses and multiply. So what we're doing is we're essentially distributing a power. We're distributing an exponent. So if I have a big old 4x to the third, yz to the third, what I'm going to do is distribute that power. So now I have 4 to the third, x to the third times 3, y to the, you could say 3 times 1, or you could just say 3, and z to the 3 times 1, which is 3. And so that is essentially 4 to the third, which, let's see, 4 times 4 is 16, times 4 is 64. So you could say 4 to the third or 64, either way, both right answers. X to the ninth, y to the third, z to the third. Oops, that's another y. That's what I get for thinking too far ahead. Z to the third. Now you could do this in expanded form, but it's going to take you a while, right? So knowing the rules is helpful, but knowing how to do expanded form will still get you there. It's not as efficient, but it works. Essentially what you have to say is, well, there are 3 x to the thirds. And so you would write it out 4, 4, 4, and then 9 x's and 3 y's and 3 z's, and then you would consolidate them together. Woo! Okay, we're going to make it. Next one says 7, this is all in parentheses, 7 x y to the negative 2. And that's all to the negative 2. So here's where you have to make a decision. You have lots of choices in Algebra 1. Am I going to put the whole thing under 1? 7xy to the negative 2, and then square all of that? Or do I want to deal with multiplying them all together? So I would have 7 to the negative 2, x to the negative 2, y to the negative 2. Oops, it's really hard to write with these. Negative 2 times negative 2. So you could do it either way. These are both the same. And you'll end up with the same answer in the end. So now I have a bunch of negative 2's, but this y right here is going to end up being a positive, right? So here in this case, I could say, well, okay, I've got 2 of each of those, but this one's going to end up going to the top, right? That one's going to go up here into the numerator. And so in both cases, what I'm going to end up is I have this 7 to the negative 2 that's going to go down into the denominator because it's on top right now, right? So I'm going to have a fraction line in my answer for all of this. My 7 squared goes down into the denominator. My x squared goes down into the denominator. But my y squared squared goes up top. And remember that when we're taking a power to a power, we can multiply those powers together. Although in this case, adding them and multiplying one would give you the same answer, right? So in the end, our final answer is y to the 4th over 7 squared, or you could say 49, 49 x squared. Okay. One more. Pause it if you need to, rewind it if you need to. I'm going to keep going. 6x to the negative 6th, y to the negative 7th, z to the 0 to the negative 2. So right now I'm just going to distribute that negative 2. 6, you can do it the other way if you want. 6 to the negative 2, x to the negative 6 times negative 2, y to the negative 7th times negative 2, and z to the 0 times negative 2. Okay, so in the end, what am I going to end up with? Let's check it out. I'm going to put my big old fraction line here. The 6 has a negative power. It's on the top right now, so it's going to move to the bottom, right? So I've got 6 squared, or 36. My x, negative 6 times negative 2 is a positive 12, so that's going to stay on top, x to the positive 12. My y, negative 7 times negative 2, is a positive 14, so it's going to stay on the top. My z, z to the 0, 0 times negative 2 is still 0. And anything to the 0 power is 1. So essentially, it's gone. It's turned into a ninja 1. It's hiding in the shadows. So my final answer is x to the 12th, y to the 14th over 36. Okay, so we're starting to combine everything, aren't we? All right, one more. I'm going to move really quickly through this one, so feel free to pause and rewind. Oh, sorry, this is our last rule of exponents. So this is the power of a quotient. Quotient means to divide. The rule says if I have a fraction or a bunch of stuff in a, separated by a fraction line, and that's all taken to a power, then I'm still going to distribute the power. So it's going to look like this. I have a to the m over b to the m. Right? And do you remember what we do then? So we could subtract those powers, right? That would be, we would subtract those powers, but they have different bases. So these are both different colors, right? Apples and oranges, or apples and bananas in this case. Okay, so let's try an example of that. I have 3/5, down the brush size, and that's squared. So that equals 3 squared divided by 5 squared. Now, in our case, we can actually do it. We can take it one step further and say this is 9 over 25. But 3 squared divided by 5 squared is a perfectly acceptable answer because we're dealing with powers and exponents, right? Okay, so that's our first example. The next example says 2a to the 5th right, 2a to the 5th over b to the 7th squared. Now you could still use expanded form and say, well, how many 2a to the 5ths over b to the 7ths do I have? I have 2 of them. And you would say, okay, well, 2a to the 5th over b to the 7th times 2a to the 5th over b to the 7th. And recognizing that this is what that means will come in handy in the next unit because it's going to get a little bit trickier still. And you could do that and that would be fine. Or we could just keep on keeping on with our rules of exponents and just distribute it now. So 2 squared a to the 5 times 2 over b to the 7 times 2. In the case up here, without the expanded form, we still have 4a to the 10th divided by b to the 14th. And then we could, with our expanded form, we could still do all this multiplication. 2 times 2 is 4. A to the 5th times a to the 5th is still going to be a to the 10th. You could expand that out and say 2 and then write 5 a's. Oh, do I want to do that? No, but I'm going to anyways, just this once, okay? Just in case there are those of you out there that really want to use this. So 2 and then 5 a's times 2 with 5 more a's. It's really hard to write small without using my wrist. And then 7 b's and 7 b's. So 1, 2, 3, 4, 5, 6, 7 times 1, 2, 3, 4, 5, 6, 7. My 5-year-old would come in at this point and say, Dad, that's not how you write B's, 2's, and A's. And I would say, yes, that's true. And essentially, we could now count them, and we would end up with the same answer, right? So we would still end up with 4, there's 10 A's, so that's a to the 10th, divided by, there's 14 B's, so b to the 14th. And that would still be our answer. So, 2 different ways to do all of these. Okay, and the last two examples from the notes, let's go ahead and do that and then call it a day. This is a 45-minute video so far, so I apologize for that. But here we go. We're going to finish this up. Parentheses, 3a to the negative fourth over b to the seventh to the third. Let's clean that up just a little. Okay, so you could expand that out. I'm not going to. I'm just going to follow the rules. First thing I'm going to do actually is get rid of my negative exponents. So I'm going to take this a to the fourth and move it to the bottom. So I've got 3 to the third that's still on the top over a to the 4 times 3, b to the 7 times 4. So my final answer would be 3 times 3 is 9, times 3 is 27, or you could leave it as 3 to the third over a to the 12th, b to the 28th. Big numbers, big numbers. If you actually wrote that out in expanded form, it would take a while, which is why we have these rules of exponents. Saves us time and a little bit of sanity. Last one, ready? A to the negative 2 to the negative 2 times b to the negative 5 over c to the negative 11, all taken to the negative 6th power. Okay, so let me show you how fast this goes once you get used to it. I know that I'm going to multiply the negative 2 and the negative 6. So this is going to be a to the positive 12th. B to the negative 5th times negative 6th is going to be b to the 30th over c to the negative 11th times negative 6th is going to be c to the 66th. Please don't write that on an expanded form. And that's our answer. We're done. So once you get used to these, it's not super bad. Expanded form will get you there, but in equations like this one, it's going to take a long time. So mind your rules. Make sure and fill out your notes so you have those available for all quizzes and tests. I appreciate that you've made it through this video, and I will see you soon in the next lesson.